Unit 1, Lesson 3, and we're going to be dealing with limits involving trig. So that's the big difference here is now we've got limits that are involving trig. I want to make sure I have the right layout here. Perfect. Okay, so I want to start, and actually let's take a second and let's take out our calculators, or if you want to take out your Chromebook, to take a look at your calculator as well, because we're going to kind of start off with a calculator question. So let's take a peek at the first limit here. It says evaluate the limit as x approaches 0 of sine x over x. While you're getting your calculator app on and stuff, the first thing that we should always really do is see if we have an issue. So the first thing I should do is say, all right, well, what is, and I'm just noticing there's a typo here. Sine all by itself doesn't mean anything. We have to always take the sign of something. So let's put an X in there because sine all by itself doesn't mean anything. Even look in the calculator on the home screen. If I type in sine, it's programmed to open up a parenthesis because it's saying of what? Sine by itself doesn't make any sense. So that's a typo. If we were to plug in 0 for X, so I have sine of 0 over 0. And you can double check that the sine of 0, oops, I typed sine twice there, is 0. So 0 over 0 is an indeterminate form. So we're supposed to do something else. Well, there's nothing to factor. There's no radical. I gotta look at the graph in the graphing calculator because I'm kind of at a loss here. What can I do with sine x over x? Not quite sure. So I want to take a look at the graph. And if you weren't allowed to use a calculator, you'd have to make a table of values. So we're lucky that we get to use the calculator. Sine x over x. This also allows me to bring up that your calculator needs to be in radian mode. So hit your mode button and make sure radian is highlighted in like the gray bar. And then we can take a look at the graph. I'm going to zoom in on mine a little bit because remember what we're approaching here is 0. So I want to see what's happening here as I approach from both sides. Now it looks like it's supposed to be going to what y value? You can hit trace and let the calculator kind of tell you the numbers there. Look at the y values, right? Yeah, it looks like it's supposed to be 1, right? Now, I don't see on the graph any issue, but we do know that this doesn't exist at 0 because there's a 0 in the denominator. Take a look at the table of values. It's not that the calculator doesn't know it. It is telling me there's an error at 0. It's that the calculator is not programmed to draw the hole in the graph. So you have to be aware of looking out for those missed points. We know that there's an issue at 0. However, even from the table, we can see that the values are getting closer and closer to 1. The graph itself is showing me that y value of 1 is what I'm approaching from both sides we're going to meet there. So the limit as x approaches 0 of sine x over x is 1. And we really had to get that from the graph. The cool thing about sine x is that a lot of our trig functions can be rewritten in terms of sine or also cosine. Now, it's not on the top, but I actually want to take a quick second and talk about cosine so you can see why I'm ignoring cosine a little bit. If I add in as another part of this do now, the limit as x approaches 0, totally new problem of cos x over x. we're supposed to just plug in. So cos 0 over 0. But let me get back to just a regular screen here. Cosine of 0, that's 1. That's not 0 over 0. So when we're looking at cosine, it's not what we would call an indeterminate form. It's just that this does not exist. It goes to either positive or negative infinity. Oops. So that's sort of why I'm ignoring cosine. Cosine doesn't have a limit exist as x approaches 0, but sine x over x did. So we can utilize that to then rewrite other trig functions. If we could go back and kind of just memorize that we know this one fact that sine x over x goes to 1, we can use that as our tool. So let's go back to the idea that we need to rewrite and look at number 1, the limit as x goes to 0 of tan x over x. Now, I can't factor or anything, but I can rewrite tangent. Does anyone remember what tangent is in terms of sine and cosine? Aiden?
It is, to I'm correct, it's sine and cosine.
Nice. So I'm going to rewrite this as a fraction, sine x over cos x. And then it's making a complex fraction. This is still all over x. And maybe to make our life a little easier, let's put that x over 1 so we can kind of see that we had a complex fraction here. One step that I did skip, and I apologize, I jumped the gun there. If I just plugged in 0, tan 0 over 0, the tangent of 0 is 0. So this is an indeterminate form. Especially for our notes purposes, I want to backtrack and write that in there so that we know that we always have to worry about that. Indeterminate form is why I was moving forward and asking, what could I do to rewrite this? Simplify a complex fraction now. Look at these mini denominators. I've got cos x, and we've got really just a 1. So I can use cosine x as a LCD, or a least common denominator. Multiply it to the top and the bottom. It cancels out on the top. And now I'm going to be able to rewrite it. Always remember to bring down the limit as x goes to 0, because that's really what the problem is asking. And then I have just sine x. And then in the bottom now I have x cos x. Sine x. And then the x in the bottom. I'm going to make this little blob. Sine x over x, like we saw in the top, goes to 1. So I can't reduce anything, but I can apply the property that as this little blob sine x over x, that's going to go to 1. So this is equal to 1 over, and then I could just plug in cosine of 0. Cosine of 0, we just went over as 1, so 1 over 1 is 1. I'm still able to utilize the concept of I have to rewrite it somehow if I'm dealing with a trig function like tangent. Let's take a look at number 2. Notice the big difference here is now I've got a constant multiple in there. I'll make it even bigger for everyone in class. Okay, so here's a little technicality. Go back to your y equals. We were looking at sine of x over x. But what happens is as long as the numerator has an x and the denominator has an x matching, it's going to go to 1. If you multiply a different constant into either location, that constant is going to kind of take over, and it will multiply where it is. So if it's in the sine function in the numerator, it's going to be times 4. If it's in the denominator, it's going to be a divided by 4. So go back and just see what happens now if I put a 4 inside that parentheses, because graphically, you're going to see this value at 0 pops up to 4. See how that maximum point has slid up?
Translation. It's like verbal translation.
Yeah, absolutely. Stretches it up there in the middle. So how could you write that out algebraically and not always resort to the calculator? One thing that you can do is I'm going to kind of formalize the blob, which is totally my phrase, but I kind of feel like you're making a blob around sine x over x. That's why I call it that, Chris.
You said that you're like trying to figure out a way to show it algebraically, but like on a test per se, like would we need to? Like would that be required?
Nope, it wouldn't. Great question.
Right.
And I want to kind of get you down to the point where you'd be able to look at that and say, oh, it's times 4 in the top, that's a 4. Because it's the sine x over x that it's up times 4, so it's going to be a 4. Oh, there's a 7 in there, it's times 7.
I'm sorry. As a translation before, but specifically that'd be a dilation
Because you're stretching it, right? Not a translation, a dilation. Yep.
And that'd be different. That'd be like adding a 4 base. That'd be a translation.
Very true. Yep. So instead of just thinking of it as x over x, if we could say that any sine of any constant x over that same constant, then I could use the property that you could write the number 1 as any number divided by itself. So algebraically, I could write this as sine of 4x over x, and I could say that what I'm going to do is I'm going to make the denominator match the 4x in the top. But if I multiply a 4 into the denominator, I would have to match that action by multiplying a 4 into the top in order to keep balance. And so this sine of 4x over 4x goes to 1, but we have that extra 4 that came into play, which is why it is being stretched up to the y value of 4. Questions? Let's take a look at another one. How does this maybe get a little bit trickier is if you throw some algebra in here that you have to watch out for. So what if we have addition or subtraction as part of our values? So number 3 says the limit as x approaches 0 of 2x plus sine x all over x. First thing you should always double check is, do I get 0 over 0? Is it an indeterminate form? Anything times 0 is still 0, and the sine of 0 is 0. So we do have 0 over 0. Okay, we have to keep thinking there's something more to do. Now, here's the problem. When we add or subtract 2 terms and make a binomial or any type of polynomial, it locks those terms together. So when we're factoring and reducing, you can't cancel through addition, you can't cancel through subtraction. Well, I can't group that little blob of sine x over x through addition either, because that x is dividing both terms, and I can't just let it attach itself to the x. So if I wanted to show this algebraically, I would have to split the fraction. That if I'm dividing both terms by x, it's really like you're distributing that division. Split them up. Perfect. Because now I've got a blob. Sine x over x is going to go to 1. And now I'm looking at this 2x over x. Well, it reduces. I could cancel out that x. Let's say for a second you didn't think of that. If you didn't think of that and you went to go plug in the 0, you're going to wind up with 0 over 0 again. Anytime you get 0 over 0, that's your, hey, you got to do something else. So then you would look back and say, oh, I could actually cancel out these x's. So this limit actually then reduces to the constant 2 plus 1, so we get a 3. Let's take a look at number 4. The limit as x approaches 0, we've got sine x over 3x squared. All right, well, I can't blob a sine x with an x in the bottom because that's a polynomial. It's all attached there. But if I plug in 0, I get 0 over 0. So I do have to think about this. Let me just write out that plugging in 0. Not much I could do with sine x on the top to rewrite, but what about the bottom? You know?
You can take the GCF of x, and then in that case, you can separate out what we talked about before, that ratio of sine x over x.
Beautiful. The bottom, we have a GCF of x. Pull it out. You got to do something. So you kind of have to kind of filter through your options. Is there anything I can do here? You can factor it. And then by factoring that out to the front, you've now legally separated it from the other terms it was locked into. And now here's that sine x over x that I can blob and go to 1. Now I can plug in my 0. So I have 1 over 3 times 0 minus 2, or 1 over negative 2. Questions? All right, let's do a few more. Ones that kind of make you say, oh no, that looks like a really difficult one. Whenever you see something sort of in this sine x over x, I want you to realize that the constants that are there are really what's driving the problem. Don't call it out loud. In your head, take a guess as to what y value you think this might approach. Looking at that, just like a gut reaction as to what you think this is going to go to. And let's use the calculator to start. And let's plug in 5 sine of 3x divided by the sine of 5x. This is a crazy looking function. That's fun. But we're really only worried about what's happening as it approaches 0. So through the craziness, find your y-axis and kind of see where it is. You can use your table of values to try and look closer, or you can try and zoom in. If I zoom in close enough, what y value is this approaching? 3. Now look back at your problem. Not the legal way of doing it, but if you completely ignore all the signs and all the x's, you have 5 times 3 on the top divided by 5 on the bottom. 15 divided by 5 is 3. It's always going to happen that way. Always. Now, I can explain it by creating that sine x over x blob. You can split this up. You can multiply things into the top and the bottom. And then after all this algebra, you're going to wind up saying, oh, I kind of could have just ignored all the trig stuff and did the work with the constants. Yeah. It's So when you have this sine x over x or sine x over sine x, the constants are dictating everything. So this is just going to be 3, or let's write 5 times 3 over 5, which is 3. Now, I can't help myself. I have to at least show you once why. Granted, on a test, you're going to be able to tell me 3 and you'll be done and right and you don't have to show the work. But I don't ever want you to just kind of trust me on something like that without at least watching why this happens. So if I were to split this apart, limit as x goes to 0, I like the 5 and the sine 5x in the bottom because that's almost a blob but upside down, right? And then I have the sine 3x, and if I split these up, that would have to be over 1. So what's missing with the 5 part of this is an x. This would need to be a 5x to get the sine x over x. Yes, it's a reciprocal, but I still need the x there. But if I multiply an x to the bottom, at the top, I'd have to multiply an x to the bottom. Well, wait a second. That x is actually needed over here. My sine 3x actually needs an x. So I'm going to do a little erase here and say, no, I need my x over here. I'm still multiplying it to a bottom. I still made x over x. I'm just strategically placing it. And then this guy needs a 3 as well. If I multiply a 3 to the bottom, I'd have to multiply a 3 to the top. Here's my blob. This guy's still upside down. It's the reciprocal. What's the reciprocal of 1, though? I take 1 and take its reciprocal.
Well, it's just 1 over 1.
Still positive 1. If you take 1 over 1 and flip it, it's still 1 over 1. Last man standing, the 3. Okay, so that's algebraically why. Graphically, you have proof. But when it comes to this problem on the test, if you look at it and say, oh, isn't this the one that I can say that this is just a 3 because the numbers simplify to be 3? Yes, that's always going to happen. Questions? Let's see, I'm at number 6. All right. Limit as x approaches 0 of 2 tan squared x over x. Now, when a trig function is squared like that, what this translates into is that we're squaring the entire tangent of x. So it's really saying this, all of tan x squared. Now, if we plug in our 0, the tangent of 0 is 0. So we do get 0 over 0. Let's split apart tan squared. If I have to do something, if tangent is squared, that means I'm multiplying tan x by tan x. Now, I said in the beginning, I really want you to memorize that sine x over x. But if you remember example 1, I'm going to scroll back a second. We really solved that tan x over x also goes to 1. I'm allowed to know that and not have to recreate that every time. So you could say, you know what, I'm going to memorize that as well, because I know I could rewrite tangent and work that out. So I can blob one of the tangents with an x. That goes to 1. But it didn't allow me to get rid of that other tangent. So I still have to plug in the 0 to tangent. The tan of 0 is 0. So this answer winds up being 0. And 0 is okay as a solution as long as it's not 0 over 0. Questions? We've got a couple of more here. 2, 3, that's it, good. I want to give you 2 minutes to work on your own. I'm just peeking at these examples. None of them are different than something that we've already done something similar to. I'm going to give you 3 minutes, see what you could do with it, and then we'll go over it.
Miss Deland,
Yeah,
can you go back to question 6, please?
yes.
Thank you.
So awkward for me not to be walking up and down the rows right now, like forcing myself to stand up here. All right, let's see how we're doing. Who thinks they have the right answer for number 7? Chris?
The answer is 6.
The answer is 6. I love it. So, quick why? We have to, go ahead, please. I would love.
So I split the numerators, so I 5x over x plus sine x over x. Or is it multiplied? Yeah, it is, okay.
Love it.
The x over x cancels, so it's 5 plus sine of x over x, which is 1, so 5 plus 1 equals 6.
Perfect. Yes, Elizabeth, right?
Megan,
Sorry.
how come you just don't make the sine of x? Because I got 1, like I see what I did wrong. How come you just don't make the sine of x over x 1 and then do 5 times 0
Great question.
plus 1?
The plus sign here is what's messing that plan up.
Okay.
Addition and subtraction, think of it as a lock. It locks those terms together. You can't cancel it when you're factoring through addition and subtraction.
Okay.
You can't blob it with the x when it's attached by addition and subtraction. So the move of legally separating the terms is by distributing the divided by x.
Okay.
Great question. Who thinks they got the right answer for number 8? Aiden?
I wasn't sure about this one. I checked it graphically, and that answer sort of around the vicinity of 1.1, 1.3.
Okay, I love that answer. So let's actually go with that. So Aiden was saying that he used the calculator because he was struggling a little bit with this one. And the answer that he's seeing in the calculator, if I hit trace, is, y equals, I didn't put parentheses around my 3x. Let me fix that.
So also, I also just divided 4 by 3, and I got 1.32, but I wanted to find out correctly just to do a little bit of challenge.
Perfect. But I want to explore this route for other people that might feel like, I'm a go to the calculator kind of student, and how am I going to analyze this when it's not looking like a perfect whole number? So that's like at 1.2, 1.3, something more than 1. So this is one of the ones where you can ignore and pull the coefficients, the multiplier in the angle and then the multiplier on the bottom. 4/3 is 1 1/3 or 1.3 repeating. To see why algebraically, it's sort of like the wrong constant on the bottom. So I want to separate the 3 and the x. I want to leave a gap in there because that part, I really need the bottom to be a 4x in order to make the blob. So if I multiply a 4 to the bottom, I would have to match that by multiplying a 4 to the top. So the blob then still leaves behind the 4/3 because I had to match the top and the bottom by multiplying them both by 4. So either way, graphically or algebraically, or a combination of graphically with then, I thought it might just be the constants, any of it is fine.
You can also, basically what I did algebraically was, I just separate out 2 ratios, 4/3 and sine over x over x, knowing that the latter is 1. And I simplified 4/3. That's basically the same thing as you did.
The only problem even with that is that I can't just pull this 4 to the front.
Mm-hmm. Oh, okay.
You're not allowed to factor something out from the angle. So it works out only in this scenario because the constants really do dictate it. But don't think of that as a simplifying procedure. That has to stay in the angle. The only way to get the other 4 is by multiplying it to the top and the bottom.
Yes, because the 4 and the x are technically in parentheses, and it'll both be multiplied by the sign, and both incorporated that sign.
Exactly. Because if you pull that 4 out, you're neglecting the fact that it was inside the sign.
Well, you can do that for primary for exponents. You can do in order to simplify exponents. If I remember correctly, the it's some sort of acronym.
I think you're thinking of the log properties that an
Yes,
exponent
that's-
comes in front,
that's-
but that's exclusive to logs, not trig.
Mhm. Thank you.
Good. All right, last one. Who thinks they got this one? Samantha? 1.82. Let's take a look at the graph. I got something different, but I want to see if maybe the graph was what was leading you there. And then a 3x on the bottom. Make sure your 3x on the bottom is in parentheses. And that, so it was a plugging into the calculator that messed you up. Without the 3x and the parentheses on the bottom, it's not going to show you the right graph. But now that I see the right graph, do we have a better guess? You're Elizabeth, right?
Yeah, Lizzie.
Lizzie, and then this is Megan. Okay, sorry.
That's the answer 4.
It's 4. Now, this is one of the ones that you could say, 6 times 2 is 12 divided by 3. It's got to be a 4. And then as long as you've got the function plugged in correctly, the calculator will verify that that's the case. Algebraically, that sine 2x needs a 2x in the bottom. So if I just leave a space between my 3 and the x, that allows me to multiply a 2 to the bottom and a 2 to the top. And here's why I'm saying it's just 2 times 6 divided by 3, because when you actually create that blob successfully, the constants are what still prevail after you blob out the sine x over x. All right. The homework is actually the next ditto in our packet. It does say lesson 4, but that's the homework. I created a Google form for you to take a picture of that and upload it, and it's due by Monday night. So if you do have questions, you can still ask me Monday. Lastly, I apologize for the 2 a.m. remind. I meant to set it up for 2 p.m. today, and I was super embarrassed. But if you want to come 10th, you can with that Google Classroom.